Good afternoon to those of you on the East Coast, and good morning still to those of you way out there on the Pacific. I'm Curtis Brown, and my name, I'm joined here today by Robin Polson. This is TI Office Hours. We're going to focus on algebra, and today we're going to be checking out some things that you guys put in as requests. And so Robin and I have kind of dug through the TI resources, and we pulled a few things, and we're gonna share some things related to questions that you have posted to us and asked us to kind of cover. So we'll get started with that in just a second. Before I do, though, I just want to continue to say, you know, I know we're in a tough situation, and we're just happy that we have the opportunity to come and meet with you guys and try to share a little bit of knowledge and try to be helpful in any way that we possibly can. So if you would, please continue to put your questions, your comments in the chats section. Robin and I will answer those questions. You know, if you want to ask something completely off topic, that's totally fine. You won't derail us completely. We'll figure out a way to answer your question in any way that we can. And certainly continue to contact TI either on our Twitter or Instagram, and continue to post and ask questions, and we'll continue to do these office hours and answer questions as we can. So let's go ahead and get started. I'm going to share my screen, and Robin, if you would just let me know when you can see my screen there, and we'll go ahead and get going.
Yep, you're all set, Curtis.
All right, that's fantastic. So the first thing that we heard a little bit about was factoring trinomials, and maybe some strategies for teaching factoring trinomials, maybe some ideas for activities around this. And so we came up with one. I found one that I was kind of interested in. And so for us to have maybe a place to start, I thought we would start with this question. Tyson is building a rectangular garden, and it's got to have a stone border, and the total area must be 96 square feet. I guess she must be living maybe in an apartment area, and maybe she's got some fixed area that she can make this garden. The garden is to be 4 feet longer than it is wide. The question is, if Tyson uses a 2-foot stone border all the way around the garden, what is the area of the garden, not including the stone border? And of course, this is show all your work. And I have down there adapted from, and that's because I'm really not sure where the original question came from. I was shown this question by a colleague of mine, or at least a version of this by a colleague of mine. And so I've made some changes to that, maybe changed the question numbers, the context, a bunch of other things. So anyway, I just wanted to kind of give us a place to start. So typically, students may try coming at this and factoring, maybe writing the edges of their garden. And so I've actually done all the work here and shown all the work except for the solution here on this page. And so I guess where I wanted to go with this was, okay, so this is great. We can set factored form equal to 0, and we can go through and have a strategy for coming up with those factors. But I kind of wanted to focus on maybe why do we even factor? What helps us about that? And why does that matter for us to try to factor and maybe come up with these two factors down here at the bottom, x minus 4 and x plus 16. I was trying to think about, okay, so what are some things we could show people about that? Of course, we know the negative 16 probably doesn't matter, and then we want to go with the x equals 4. We could go ahead and show the solution, and I'll do that real quick. We find that the area of the garden is actually 32, but where I want to focus is back over here on the x minus 4 and the x plus 16. Why do we even come up with those? How do we show kids that that's an important thing to do? So I'm going to open up TI-Nspire software here, and I'm going to look at zeros of a quadratic function. This is a lesson on the TI website under Math Inspired. And this really is just kind of giving them a visual to play with and make some notes about things that happen. So let's navigate to page 1.2 and we'll talk a little bit about some of the things that you can notice. So what we've got over here on the left-hand side, we've got two linear functions, which are x plus 1 and 2x minus 2. If you multiply those two things together, you're going to get a function that is 2x squared minus 2 if you make this multiplication happen. But what I want you to do is let's observe what happens as I change the factors in each of these linear terms. So let's change the blue one just a little bit. I'll drag this around. And I want you to notice something. Robin, maybe you can make a comment about something that you notice is true about the graphs of those three functions as I change that blue one. What's something that you notice? Robin, are you on mute?
I was muted, yes. And you're putting me on the spot.
That's okay. What do you notice?
Well, I noticed that my parabola is changing accordingly and the blue line is changing.
Okay.
The green.
What's common about that red
sliders.
parabola and the blue parabola? Or the blue
line.
We've got
intersection points.
zeros,
The what?
right? So where the 0 happens,
zeros, yeah.
Minus or 2x plus 3 is the same place as one of the zeros on this quadratic function. Now it's 4x squared plus 2x minus 6. That 0 is at the same location. The same thing happens when I grab and drag the green one. I notice that the 0 of this green line is equivalent to one of the zeros of that parabola. Now it's interesting. So we often probably go to, and most of us do, and I did when I was teaching this. I told my students, okay, we need to solve this and we need to factor and we need to set it equal to 0 so that we can apply what we call the zero product property, right? So that, if one of those is equal to 0, then the other one maybe isn't equal to 0, but the whole thing will equal 0 because if we multiply by 0, you're going to get 0. So we say, okay, we're going to set it up and make it equal to 0, and then we'll just break this into two pieces and solve each one of those two terms for 0. But I don't think I ever really communicated with my students that the reason why that even is something to do. What we have is two linear terms that we're multiplying to make a quadratic, right? And so what I'm thinking is, I think it's pretty cool that we've got a linear term that we can graph and another linear term that we can graph. When we multiply them, we get this parabola. But the solutions or the zeros for that parabola are also the zeros for each of those two linear terms. And I think that's a pretty useful and interesting thing for students to kind of explore and play with. And see kind of why we want to factor and come up with linear terms and solve for zeros. And I think that was one piece of this puzzle that I wanted to kind of share a little bit about with you guys. Now, kind of as another option, and I know this really broad kind of topic, factoring trinomials. I mean, there's lots of things that we could go to. And maybe a lot of people have seen things like this before. I wanted to kind of just be sure that everybody was aware. We also, in our building concepts project, so there's a project kind of for middle school where we tackled a whole bunch of different things for middle school. And one of those was recognizing quadratic functions and looking at quadratic functions. Now, Robin, you probably recognize these as algebra tiles, right?
Absolutely.
And so these are algebra tiles and that you can kind of play with. And we set up this problem to allow students the ability to kind of play with this quadratic function, which is x squared plus 3x plus 2. and put it in a whole bunch of different variety of ways, and checked to see if what they in fact have are equivalent expressions for that same trinomial x squared plus 3x plus 2. And so there's all kinds of different varieties of ways that you could actually try to factor this. And the cool thing is as long as you have a certain color, each of the pieces that you couple will be coupled together. So now I have this term that would be, what is this? X squared plus 2x. And then if you look at this, this is the quantity x plus 2 times 1, right? So we have x squared plus 2x plus x plus 2, which is an equivalent expression, right? And so we could go through a variety of different ways of kind of recognizing that visual, that expression. So that was just a couple of ideas for factoring trinomials, kind of getting an idea, getting things that we could start to play with and start to try to recognize some of those factors. Now, Robin, you and I were chatting just a minute ago, and you said you had a couple of ideas of things that you also shared with your students. So maybe I'll give you a chance if you want to go ahead and try sharing your screen, and then you can kind of take us from this place to what you were thinking.
Okay, let's see. Do you see my Nspire?
I do.
Okay, that's not what I wanted to show you, but I wanted to make sure I was sharing my screen. Okay, well, I got thinking as Curtis and I were planning this, and I looked at the previous slide about ways that I taught factoring when I was an Algebra 1 and Algebra 2 teacher not too long ago. And I made sure that my students knew how to factor by what I called product sum. And so I took that problem that Curtis had, and I wanted to show you what I used to show my students on their calculator with factoring with product sum. So if we have this x squared plus 12x minus 64, we've probably all talked about how the kids need to find two numbers that multiply to negative 64, that's the product, and add up to positive 12, which is the sum. So I made them do everything by hand, of course, but you know, as some of these problems get bigger and more difficult, especially in the Algebra 2 realm, kids would start to get really frustrated when they had to try to guess and check and just figure these numbers out. So I said, well, let's use our technology wisely. So let's see if I can now get back to my Nspire. Okay, so what I'm going to do is just start a new document. And I won't save my old document. And I'm going to cancel that. And let's get a graphing page. So what you can do on a graphing page, and you can do this on the 84 as well, and I can switch back and forth, is if you take your product, so what was my product in this case? Negative 64, and divide it by x. And what we'll get is a graph, which is really kind of, I also thought of this transition in that I'm going to be talking about graphing rational functions as well. But you won't see it well. You'll just see the teeny tiny corners, which is okay. And the kids have to get used to that. Like, we don't care about the graph this time. What we really care about is that table of values. So if now I do Control T for table, my table, as I scroll through, now shows all the factors, pretty and not, of negative 64. And so then what my students start to do, and I need to apologize, I need to move our faces out of the way here. What our students do is they'll say, oh, well, was my sum, if I'm looking at 8 and negative 8, that gives me a sum of 0. That is not the sum I was looking for. And so I've now factored negative 64, and I'll scroll through until I get the sum that I want, which in this case was 4, right? No, 12, sorry. So I need, oh, here I've got negative 12. So we have that conversation. What would I do to those numbers to get me to my positive 12? And then they'll just switch and find the negative 4 and 16. Curtis, have you ever seen that before?
That's actually really cool. I don't ever thought of doing that before. Is that something you can do on the 84 as well?
Yeah, absolutely. So if I switch over to my 84, I'll just go to y equals. And again, I need to move our faces out of the way, sorry. And I'll type negative 64 divided by x. And here I don't even care about the graph. The kids get used to that at this point. I'll just do second table to look at the table of values. And again, here are all of my factors of -64. The kids scroll through until they find the numbers that give them the sum that they need. And again, in this case, it's 12. So it's -4 and +16.
That's kind of a cool way of kind of getting them to discover some of that. I think you could really use that that idea. Okay, we're trying to come up with this. We know how to multiply these two binomials together. We're trying to kind of undo that, if you will. So what are some things we need to think about? You could kind of give this to students and not really just tell them exactly what they're looking for, that, hey, you're looking for something that sums to this or whatever, but you can just kind of plop them in there with this. I think that would be really an interesting way to get them going with that. That's cool.
Yeah, it really is. And again, it's a transference, I guess, from going from paper, right? They would make these tables on paper, try to come up with the factors of -64. And then after a while, that gets a little tedious. And, one of our standards is use technology wisely. And we had this technology. And so I taught them how to do that. And then from there, if I can go back just to the PowerPoint real quickly, which you can see it. So it's not quite as fun. But what we did to factor is then we split the middle. Lots of people do guess and check, and I used to teach with guess and check or unfoil until I went to a conference and someone showed the split the middle with product sum. So I've taken that -4 and 16. I've changed +12 to something that's equivalent, -4x and +16x. Now I factor each half, or factoring by grouping, right? As we get into connection from 8th grade or algebra factoring up into higher level factoring. When you hear factoring by grouping, now it's consistent across the board. We're not one year saying unfoil, the next year saying factor by grouping. It's always just factor by grouping. So then they divide. So common factor on the left and right, you can see is x -4, and there are your factors. This is one of those processes that probably 10 years into my 25-year teaching career rocked my world. It was just this aha moment, and it's a really nice way. And then when you work it backwards, showing kids about double distributing and not having tricks, but you're always just distributing when you're multiplying. So
that's nice. Hey, Robin.
Yeah.
You just reminded me of something.
Of course.
Do you mind if I share my screen real quick?
Not at all. I'll stop sharing mine.
So this, you can see mine, right? So yes. The screen right here is out of the building concepts file called Using Structure to Solve Equations. Another one of the building concepts lessons. And this one is all about recognizing that structure. And so what you were just talking about with recognizing those factors and how we can pull those out and do that is one of the things that is emphasized greatly in this. Now, this is kind of a little bit of a rabbit trail from our factoring trinomials, but it's a related topic if you think about how we might want to solve this problem for X. A lot of students and teachers, myself included, probably the natural thing to do here would be distribute, right? I mean, we would just, well, I got 8x. Okay, so let me multiply this out and I can get 8x plus 72 minus 3x minus 27 equals 90 and try to combine like terms and do this mess. Unless we kind of recognize that idea that, hey, x plus 9 is common to both of those terms of this problem. So I can select that and say, hey, I know that 8 minus something, 8 minus 3, both of those times something needs to equal 90, right? It's really 5 times something equals 90. And so we could select that and start dealing with that piece on its own and go through there. So I just wanted to pull that up and share that real quick. Robin, you can go back to sharing your screen, but just another thing that kind of struck me.
No, and that was it for me. And what I love about that is we just showed that one process is so consistent throughout math, right?
That's, yeah, for sure. I mean,
find all these representations. It just helps kids. And it really helps me as a teacher because you know, I'll confess, when I started teaching, I taught the way I was taught, which was just process, right? Process, learn the process, get really good at the process and move on. And so once I started, you know, getting a lot of professional development and getting the concepts under my belt, it changed my world as a teacher, but it certainly helped my students be much more successful and enjoy math more, because it wasn't just a set of rules that they didn't understand where they came from.
That's right. Absolutely. I think that's seeing those connections across, you know, what they did in 6th grade and what they did in 7th grade and how that set them up for what they needed to do now, I think is huge. And I don't know, I love that we're being able to see that kind of going through this. Okay, so our next kind of piece here was for us to tackle, let's see, you already did this, graphing rational functions. So we had another request kind of coming through. Okay, so is there some way that we can help our students be able to make good and conscious decisions about graphing rational functions? What should they be looking for? What are some things that they could recognize? So I'll leave the next bit up to you.
Okay.
If you're ready to share your screen there.
I can do that. All right, let's get, is that where we were? Yep.
All right.
I'm not gonna go into PowerPoint mode because I'm gonna be flipping back and forth with.
I think that's great.
So, yeah, so I took this from an Algebra 2 teaching standpoint, just because that's really, other than some basic rational functions, that's where it's emphasized the most. At least I'll tell you, my background is in New York State. I taught in New York my entire career. And that's where I actually pulled the sample problems from. So again, I always started with the parent functions, you know, here would be 1 over x, and taught transformations on those. And then we needed to elaborate some more. We did lots of pen to paper and then used our technology wisely again. And this time of year, I keep thinking about getting ready for assessments. So while this isn't a typical year and most assessments aren't happening, it's still that time of year when you be getting into some higher level questioning. And so I took 2 questions that I found on some old, well, actually not too old, just this past January's New York State Regents exam. And so I've got one that's a multiple choice that you can see, and then we'll do another one a little bit later. And this is an example of a question where I would certainly, we'd have really nice conversations. Why can't x be equal to -2, and talk about that. And hopefully by assessment time, they're well aware of that. We talk about asymptotes and everything. But then we start talking about test taking strategies, whether it be a state assessment or an SAT or any kind of high stakes exam. You want to be able to be efficient in your test taking because they're timed tests. And use your technology well. So this one really stood out to me as, hey, if I can graph these, because I'm sure that the intent when this, am I muted? No, sorry, I saw the word mute. I'm sure that the intent when this was written was to do some really nice algebra. I would graph it, and I would graph the original problem, and then I would go through the choices and see which graphs matched. And so I just wanted to show that procedure, and then we could have a conversation about it. So again, I taught with the Nspire at the end. Anything I do in the Nspire in an F1 of X can be done in a Y1 or Y2 equals the 84 as well. So I'll go to my Nspire. Let's see. Maybe. Hold on. My apologies. Oh. Did I lose my screen?
You just closed the PowerPoint.
Close my little window. So you're all going to see that this is my first time sharing screens on a live thing. Are you back to my?
Now you're good.
Fantastic. Okay, so I'm just going to add another graphing page. And I'm going to put in that original problem. So some quick, if you didn't know, Nspire tips, I need a fraction template. Fractions mean division. I would say that to my students. So if I control divide, That's where I always found my fractions template, again, because it hammers home fractions, mean, division. And it was just my way of reminding kids of some of those little things. So my numerator, 2x squared plus 5x plus 8. And my denominator is x plus 2. And so there's a picture of that function. And again, throughout the school year, we talk about some different things, asymptotes and whatnot. Here, I'm wondering which of those is an equivalent expression. And so something I learned recently, Curtis, I don't know if you knew this, is that at least on the SATs, all the questions, answers in multiple choice are in value order. Lowest values part choice A and the highest is F. And so it's smart to start in the middle.
Yes, always.
And so recently, yeah, so then you can eliminate choices faster. So
Right.
anyway, I just thought that that was really interesting to throw out there. So I'm going to graph choice 2. I do know what the answer is, but I won't give it away. So I'm going to press tab to get my next function up. And choice 2 is 2x plus the fraction 7 over x plus 2. And you can see that they are not the same graph, so that is not the right answer. You, of course, could also look at the table of values. Now, what's interesting here is you won't see the full table when you split screen. But if you do another little Nspire trick for Nspire users, if you control, I never remember which it is, 6? Yeah, it pushes that table to another page. So now if I go to the next page, you can see that my values are not the same. So those are not equivalent expressions.
That's a really, that is one I didn't know. So thank you for teaching me that tip.
Control 6 or control 4?
6.
Yep.
I knew Control T to get a table for the split screen and, you know, quick table, but Control 6 is really nice to push that over to the next page where I can see everything.
Yeah, it's really nice when you have multiple functions that you're comparing.
That's really good.
Back to my previous graphing page, and I'll tab, up arrow, and I'm going to edit this and try choice 3. So choice 3 is 2x plus 1 plus 6 over x plus 2. And now I'll move that label around. They appear to be the same, right? But again, if I look at my tables on the next page, the tables have changed accordingly because those pages are attached. And you can see that those y values are the same, no matter how far I scroll.
That's pretty cool. Can you do?
What?
Here's another trick that I learned the other day when I was trying to think about how to show two graphs were equivalent. So I love the table of values idea here. Go back to the tables or go back to the graph screen really quick. And use I'm probably stealing your thunder, so
No, not at all.
But press menu and go to the trace and go, instead of just trace, go to trace all. This is a really nice feature because now in the lower right-hand side of your screen, you can see the value of F2 and F3 at the same time. And as you move around the screen there, you can see those values. Now, if you go off screen, it doesn't move with you off screen, but you can see the value on screen and see that those trace and are equivalent. You can also type in a value if you wanted specifically to jump to, I don't know, x equals 3 or something like that. You could type that in directly and use that. So that's kind of a fun little feature there.
That is, and I didn't know about that one. So you just taught me something too.
Hey, look at that.
Gotta love the office hours.
I do too. It's great. It's a great opportunity for all of us to learn.
Yeah. So do we have any questions out there in chat?
Haven't gotten any questions just yet. We've got a few viewers here going. So I think you're good to move on to the next question. And let's
move on to the next one. Okay. So again, so in multiple choice, time saving, always graph. And I always had my students graph. One of the things I learned a long time ago is every equation has a picture, right? So every equation has a graph, whether you're told to graph it or not. It's a great idea to graph, to see what's happening. And it really helps students make some really nice connections. So, all right, let's see if I can. Oh, Curtis, you know what I did earlier when I was being a spaz is I closed my PowerPoint altogether.
That's okay.
Do you mind sharing yours?
I can do that. Give me just a second here and I will share that. While I am doing that, I'm going to put out there what you were just talking about with the idea of graphing and getting your students to always graph. One of our good friends, Tom Reardon, kind of has a phrase that he talks a lot about, and that is that he always tells students to think graphically. If we can get our students to think graphically, and I know for me, it's always about, I can draw a picture of whatever the scenario is. Even with the question, the garden question earlier, it really helped me to kind of draw a picture of the garden, but that's like thinking visually. And what you're talking about, and I think it's very important, is to take it a step further and really even think graphically. How do these two things relate? What's the picture that we can kind of see based upon that? So I'm going to catch up with us in the PowerPoint here, graphing rational functions. And I think you are on
right there.
Number 2 now.
Yeah, perfect. So again, so when we talked about this, we wanted to talk about a little bit of basic graphing, but then also an application of a rational function, because students will often say, really, when would I ever use this again? And sometimes they feel somewhat convoluted, and this may or may not be convoluted, but at least it's a problem that might seem more real to kids than just saying, hey, do some graphing of rational functions. So here we have a problem. Again, this was from January's New York State Regents exam in Algebra 2, where Sarah is fighting a sinus infection. Her doctor prescribes nasal sprays and antibiotics. And so what they've done is they've assigned rational functions to a nasal spray function, N of t, and an antibiotic function, A of t. And this is a 2-point question, or 2-part question. The first part is to determine which drug is made with a greater initial amount of active ingredient. So this has so many parts. And again, throughout the school year, and as we're learning and teaching rational functions, you talk about initial conditions and y-intercepts and things like that, but that might not be so obvious with these rational functions. And so again, I do believe that the intent of this question was for them to solve these algebraically, replacing t with 0. So at 0 time, when you're starting, what would the starting amount of the active ingredient be? Again, in my world, I prefer a graphing solution. So Curtis, can I take back over?
Yep, if you hit share your screen, you should be good to go.
Oh, there we go. And again, I'm going to stick with Nspire unless there's anyone out there in the crowd that says I have to go to 84. I'm happy to do it there as well. So I'm going to just start a new document and not save my old one. And again, I'm going to add a graphs page. So my first function is pretty big. Now, something that, again, this is more of an Algebra 2 style question that your kids get used to is, on your technology, if you're on the 84, you have y equals, and you're going to graph in terms of x. And on the Nspire, it's f of x equals. And again, you need x's. So they need to know to replace the t's in the problem with x's. It's not a big deal once you've gone through enough of these, but just little things to think about. So I've got the fraction x plus 1 over x plus 5. I'm going to add to that the fraction 18 over x squared plus 8x plus 15. And what's really nice is this, algebraically, these are also factorable. So it's really kind of neat, Curtis, how all of this ties in to kind of one big major topic, right?
Yeah, I mean, it's cool how, we've really kind of continued along that same thing. And I think our last topic that we're going to get to in just a second is also going to relate a little bit to this. So I think all the way through, we're going to see that factoring bit.
Yeah.
pop up over and over again.
Yeah, it's pretty fun. So here you can see that the y-intercept, or the initial condition, is somewhere between 1 and 2. And at this point, I don't really care what it is. I just want to look and see which has the greater one, because that's what the question is asking. So I'm going to press tab to get to my next function. And fortunately, this is smaller. So I'm going to do a fraction. And this is 9 over x plus 3. And there you have it. So you can see that this function had a larger initial condition than the first one. It does ask what it is. Actually, it does not ask, it just says which it is. Justify your answer. So I would sketch a graph, circle it, and say this one's bigger than that one. If you do it algebraically, you get a larger value. This one's nice too in that it's 3. You can actually see that it's 3 with your grid.
That's really cool.
Is that neat?
That is. That's pretty cool.
Yeah.
Nice.
So then on the next slide, which I'll show you, I'll have Curtis show in a second, but I'll just talk through it because it's kind of cumbersome if we go back and forth. It asks, she's told to take the drugs at the same time. How many hours into taking them would the effect be the same? So that's just a matter of setting these equations equal to each other algebraically, if you're doing this algebraically, or finding intersection points if you're solving graphically. So to find an intersection point, we'll just press menu, analyze the graph, choose intersection, go lower bound, upper bound. There it is. At 8 hours into taking this medicine, you have the equal effect. There you go.
That's cool.
Yeah.
Right. Really quickly,
Yeah.
Robin, I just want to remind folks that, hey, they can be posting questions to us. If they've got questions around this stuff, that'd be awesome. Or again, like we said at the beginning, you can make questions that are unrelated. So Robin, if you stop sharing right quick, then I will.
Absolutely.
Sharing, that'd be good. And then, yeah, so here's that question that Robin just finished sharing. And then our next and last topic for today is graphing conic sections. This is something that we got some questions around. Some folks wanted to know a little bit more about graphing conic sections and how do you do that on both platforms, TI-84, TI-Nspire. So Robin, if you want to tackle, if you will, some conic section graphing, I think that would be good. Here's some graphs or some prompts that you could use. So I'll let you try to graph a few of those and show us a little bit about how to do that.
Yeah, absolutely. And there's no need to go through all of them, but again, just a little bit of background. By this point, asking a question like this, the first thing my students should be able to do is look at each of those and know what they are in general. So the first one, they notice that both x and y are squared and the coefficients are the same. So they should know in their heart that that's a circle. So when they graph it, they had better see a circle, right?
Right.
Part B is a parabola because only x is squared. C, both x and y are squared. They're being added, but the coefficients are different. So that must be an ellipse. I used to call that a squished circle just to make those connections between a circle and an ellipse. And then because there's subtraction in between the two squared terms, it's a hyperbola.
We used to talk about the relationship between circles and ellipses and talk about that the circle really is just a special case of an ellipse where the major and minor axes are equivalent. So that was always a fun thing because I like to show my students that the area of a circle was really the same equation as for the area of an ellipse. You just had it mashed together. So I'm going to stop sharing if you are ready to share your screen there, and you can kind of walk us through a couple of.
Sure. And I'll show both platforms here. In fact, do you see my 84?
I do.
Excellent. So because I have talked a lot about Nspire, that's the last thing I taught with, I'll give the 84 some credit here. The 84 does have some preloaded apps when you get it, or as you update your operating system, and it's always really important to update your operating system on your handhelds. That's always a free feature off of our website. So when you press your apps button right here to the right of math, you'll see choice 4, there is a conics choice. So if I choose number 4, conics, there are my 4 conics sections. So let's just say I'm thinking that part C, number C on that first last slide was an ellipse. So I'm going to test that. So I'm going to choose number 2 ellipse. And notice it gives me, oh, I don't like this. Ha! This isn't what I was expecting, Curtis.
That's okay. It's in the.
Oh, I love being live. Okay, so we're going to wing it. So let's say I have an ellipse in one of these forms. I'm not, oh, I see the difference.
Some cool things about this form, Robin, and I'll just kind of talk you through this real quick. There's some really cool stuff here. Notice on the right-hand side, the red and the blue, you have an ellipse. One of them is vertical and one of them is horizontal.
Right.
Oriented. I like that because that helps my students recognize which one of these two things I have.
Yep.
Notice that I have my major and minor axes underneath of there, and I can talk through the forms that I expect when B is underneath of the X squared portion, or if B is underneath of the Y squared portion, and we can talk about what does that mean in terms of the shape I should expect. So either one of those, I can't do this on the top of my head. I can't do this off the top of my head, translating that.
Oh, the rearranging?
Into giving it the translated form. But let's.
Oh, me either. So let's just pretend.
Yeah, let's pick one. Number 1.
All right, so I'm going to choose number 1.
Yep, we're going to have a horizontally oriented ellipse.
Yep.
Let's give it some coefficients. Let's give it that actually 3 seems pretty reasonable.
Yep.
Let's go with B is probably, let's call it maybe 1. Let's go with that. And then I like kind of having a center 1, -3. I think that's fine.
I think so too. And
let's graph those.
And the one thing I want to mention is these are hotkeys, and in the software, the screen would be above your keys, right? And so this graph would be above your button graph. Sometimes people get a little confused on the software with that. So if I press graph, there is my pretty ellipse. Very nice.
So that gives the students a way to kind of manage that graphing of that conic. Note that we didn't have to solve for Y in terms of X. We could put this into kind of a fairly generic form that we're used to seeing. We don't have it in standard form, but we did have it in a translated form, and so that was kind of so we could see that ellipse happen there. We could do the same thing with the vertically oriented ellipse, but I think we've kind of seen how that works. There are some really some fun pieces in this graphics piece as well. You can do some analysis on the conics graphing app. That's really kind of cool here. But I think the question was really more about just graphing and getting those graphical representations up. And so
absolutely.
There you go.
Can I switch to Nspire?
You can.
All right, so I'm gonna switch to Nspire now. And I'll just add a new page to whatever I was doing last time. And again, we're
I think you're only sharing the 84, so you'll need to switch to.
Oh, how did that happen?
That's all right. Just choose.
Hold on, I know what I'll do.
Yep.
I know why. Are we back?
We are.
Great. So on my Nspire, I'll add a graphs page to my document. And I'll go back to that original ellipse. But with the Nspire, if I delete my equal to sign, notice now this is where I can graph inequalities and relations. And then you can have that conversation with your students about why do I choose relation when we're talking about these conic sections, which is fantastic, failing vertical line tests and whatnot. So now I can type that in exactly as I see it. X squared plus 2y squared plus 4x plus 2y minus 27 equals 0. Beautiful. Nice, quick way to graph some conic sections, or anything for that matter, any relation.
That's awesome.
Yeah, quick
Hey,
and easy.
Robin, I'm gonna steal
Yeah.
the ball for a second.
You're gonna what?
I'm gonna take this away from you. So if you'll
Oh,
stop
absolutely.
screen right quick. I am going to share my screen real fast because I wanted to show, so you showed the relation graphing power and the ability to type this in terms of a relation, but there is another option for showing showing conic sections. And so if you go underneath of Nspire and you click on the graph entry edit and choose equation templates, so it's option number 3, equation templates. You have equation templates for lines, parabolas, circles. So some of those conic sections in their translated form. You also have the option for conic directly typed in this form. And so that gives us the option. So that one ellipse, we can now check it
Right.
just a minute ago, right? And type that in as 1x squared. Let's see, we don't have any xy terms, right? So
Yep.
you have a y squared, which is 2 for x, 2 for y, and minus 27. And we can get that graph that you just showed just a minute ago, which is kind of cool.
Nice.
Gives us a good way to mess with conic sections even in a more generic way. So there's a couple of ways we can definitely navigate.
Yep.
Navigate
And
that.
now I'll tell you, I didn't teach pre-calc for several years, so I'm not as familiar, but I'll put myself out there. You can also, and Curtis, you may know better than I do, in a geometry page on the Nspire, deal with your directrix and focus and
Absolutely
that way. So there's a lot of different ways to approach conic sections, which is great because it's a higher level topic. And so you tend to want to approach it from many different perspectives.
Yeah, you can use those geometry pages and explore kind of the locus definitions of each of those. Is, you know, the sum of two, some of the distances from a point or 2 points, and the focus directrix, all of those different pieces that you can do. So that's really a cool way that you can navigate this. So Robin, I'm not seeing any comments in the chat, no questions that we've seen. We've had a few viewers this morning, so that's really good. And I'm super happy that we get to do this, and we've kind of been able to answer a few questions. So again, if you are watching this, please continue to comment in the YouTube comment section there and ask us questions, or contact us through our Instagram or Twitter accounts. They're at TI Calculators. Otherwise, Robin, I think we're ready to sign off, and we'll be back again to do another office hours tomorrow afternoon, actually. Tomorrow.
Yes.
So,
tomorrow, AP Stats tomorrow night.
AP Statistics tomorrow night. All right. Well, we'll chat again soon. So.
All right. Be well, be safe, everyone.
All right. And be safe.
Yep. Take care.